Hi everyone, this is going to be a quick tutorial on how to run BLAST on the command line. So before we did a BLAST search where we would BLAST against a database online using some protein of interest. So today I'm going to show you how to do that. Let's just dive right in. So the first thing we're going to need is a database. So in this case, in this example, we're going to be blasting the Saccharomyces cerevisiae genome against the Uralia genome. So let's have a quick look. That means we're going to be using Uralia as our database. And so here is our database. You can see it's a FASTA file with a series of gene names and gene sequences. So that's our first step. We want to have a FASTA file like that for the database. We're now going to format that database. We do that just like this: format DB, and then the name of the database. Oh, I messed up. So format DB, and then dash I for the input file, and then Uralia.pro. Okay, so if we look, we now see that BLAST has automatically created 3 files. So we're never going to look at these files, but these are the 3 files that contain the database. Basically, when we ask BLAST to blast against this database, it's going to go look for and use these files. So all we need to do is what we've done: format db-i and then the name of the database, and everything's created for us in the background. Okay, so the next thing we need is an input file, a file that we're going to blast against the database, and we have that here with the Saccharomyces cerevisiae proteome. And again, we see it's a similar thing with gene names and gene sequences. So when we did this online, we did one protein at a time. So that would be like taking this protein and blasting it against a database, and then taking this protein one after another after another. So one of the nice advantages here is actually we can, with a single command, we can blast each one of these against the database. But there's no magic that's going to happen here. It's going to do it exactly like it would if we did it by hand, one after another after another. Okay, so we're now ready to do a BLAST search. So the way we're going to do that is we're going to use BLASTALL, and now we're going to pass it a variety of arguments. So BLASTALL is going to need several major arguments. It's going to need an input file, it's going to need a database file, and it's going to need a protein. Today we'll also talk about -m, which will tell us the format of the output, and we'll also talk about -e. So let's start with this. So the way that it's going to work is we're going to use each of our arguments. So -i, our input file is cerevisiae, and then our database file is Uralia. In this case, both sequences are protein files, so we're going to use a BLASTP program. So we're going to put -p and then BLASTP, and that's all we need. So if we blast that, it may take a moment actually, but you'll see, so just like any other program, it's just going to spit this to the screen if we don't tell it where else to put it. So instead of that, let's go ahead and put it in an output file. And I'm going to use this ampersand to run it in the background. That basically means it's going to keep running even when we click. It will run even though the command line comes back. See? Usually when you run a program, if it's still running, it won't let you go again. But now we've got another line here. And this is just useful because now we can use this to look at our BLAST out. So this is the standard output for BLAST. And let's just look through what this says bit by bit. So first it says BLASTP, telling us what program is being used. This is the program. This is the paper that reported this program, and here's an update of that paper. So that's just sort of telling us what references this BLAST program is using. That's just where they reported BLAST. So then we have our query sequence. So this would be our cerevisiae sequence, and it tells us that it's 104 letters. And then it tells us that it's blasting against the database Uralia.pro, and tells us a little bit about that. So for this first protein, which you notice is a fairly short one, it did a search, And then it found actually that there were no hits, so it did not find any Uralia proteins that are related to Cerevisiae. So that's the result for our first search of this protein. It didn't find any significant results. Okay, so now what we see this next line, we see again BlastP 2.2.6 as we saw at the top. So this means this is our next entry. So I'm just putting that at the top, and then we can see the same stuff. BLAST 2.2.6, the two references, and then the query. So now this is our second query. You'll notice it's different. It has different length. And again, blasting against the same database, searching. And in this case, it found some hits. So what we're looking at here is the hits that it found in order. So the best hit it found was this gene. The second best hit is this one. The third best hit, and so forth. And then we see over here that we have the e-value. So we talked a little bit about the e-value. The e-value is basically the chance that we would find this good a hit. So for this, for each hit, we get an e-value. The e-value tells us the probability that we would have seen a hit this good entirely at random. So something like 0.5 is not very inspiring because it means that the chance basically that this protein and this protein show a little bit of similarity is so low, the chance is about 50%. The degree of similarity is so low that it could just be random. And we'll see that. So now let's skip down to our next part. So notice we have our 4 hits, 1, 2, 3, 4. And now we're going to have 4 entries starting with the caret. So let's just take them one at a time. You'll see that the hit here is the same as the first. And so this is showing us the bit that aligned. And so it gives us a little bit more information. How many bits of score we got. That's just the overall BLAST score, the expectation, and tells us some things about the methods. Notice here it tells us how many identities it had, 11 out of 18. And then positives are amino acids that are similar to each other but not identical. And so here we have our alignment. And so what you can see is, there are about 11. There are 11 amino acids that are shared, but it's a very short sequence. There's a lot that are different. You can kind of see why BLAST wasn't all that inspired by this hit, that it says that it only has a expectation value of around 0.5. Okay, so this first entry then goes with this first protein in the list, and you'll notice the second entry goes with the second protein in the list. And if we scroll down, we'll see 3 and 4. Okay, so let's just look at what this looks like when we get a really good hit. So I'm going to just flip down for a few until we find one that's a really strong hit. Okay, so let's look at this one. So again, we see the same, the BLAST, and then the reference, and then the reference, and then the query. And so in this case, we see 4 hits. But if we look at the first one, we see it's a remarkably strong hit. 620 bits of score with an e-value that's so small that they said 0. Basically, the chance that we would find 2 proteins this similar as this one and that one is just about 0. No chance. And so we can see that when we look at this first alignment, that we have a huge degree of similarity. So the main thing to see is here's a BLAST out where we have really strong hit. And the second thing I'll point out here is all these X's. So these X's, that means that our protein has been filtered. So this would be probably a repetitive region. You can see this region has a lot of G's in it. This region was probably just G-rich. And so BLAST filters those out. Before it does the BLAST, it filters them out. So just in case anyone was wondering about those X's. Okay, so that's our standard